As you might have noticed, we're going to be talking about the structure of the atom and a little bit of the theory. Yeah, a little bit more of like the theory behind the atom so that we can justify some physical observations about the atom. So let's talk about the Bohr model. Okay. So there's a lot of history behind the formulation of the atomic model, which we don't really need to go into, but I do want to talk about one major historical milestone, which is the Bohr model. So basically the idea behind the Bohr model is that there's three major particles in the atom. And these particles are the proton, the electron, and the neutron. So the protons are the positively charged positively charged particles I'm pointing to with my mouse. The electrons are negatively charged, and neutrons are neutral. And basically, what holds together the atom is the electromagnetic force. So you know that opposite charges attract. So the positive charges of the protons attract the negatively charged electrons. And this force can be described by Coulomb's law, which I'm going to just write down. Okay. So Coulomb's law is, so force equals Coulomb's constant times charge 1 times charge 2 divided by the distance between them squared. Okay. So as we start talking, so maybe in later lectures, it's important to kind of know this law. Okay, let's go back to the presentation. Okay. So another big idea behind the Bohr model is that we have these orbits. You can see these little circles that the electrons follow. So the idea is we have these different like levels, sort of like these energy levels that the electrons go into, and the idea is that they like go around the nucleus in these circular orbits. Okay. So let's talk about the nucleus for a minute. So knowing Coulomb, so you know that opposite charges attract and that the same charges repel, right? So you might be wondering, how does the nucleus actually stay together, since we have all of these protons together in the same area, which are all repelling each other. So the protons and neutrons, which we call nucleons, are all bound by the strong force. So yeah, and this is kind of more into physics, so you can look into this yourself if you want to. So basically, although the protons have some repulsion on the atomic scale, the strong force is much stronger than the electromagnetic force, so it holds the nucleus together. And the number of nucleons determines the properties of the atom, really, since the vast majority of the mass of the atom is in the nucleus, right? So the mass of it, so by the way, so a neutron and a proton weigh basically about the same, and an electron is about 1/1800, like the mass of a proton. So if you want to determine the mass of an atom, all you have to do is add the mass of the number of protons plus the number of neutrons. So basically the total number of nucleons will give you a rough estimate of the amount of mass in the nucleus. Okay. So I also want to talk about how the number of protons and neutrons matters. So the number of protons is given a special name, which we call atomic number. And let me see if I can pull up a periodic table. Okay. So I don't know if you can see this. The little number on top of the symbol, on top of the element symbol, is what we call the atomic number, and it describes basically how many protons are in the nucleus of that element, right? So during chemical transformations, since the element, if the element will remain the same, so the number of protons will also remain the same. Okay. So then what does the number of neutrons determine, right? So the number, if we have two nuclei, let's just imagine we have two nuclei and they have the same number of protons each. So let's just say they each have 6 protons, right? So let's say one of them has 6 protons and the other one has 8. One of them has 6 neutrons and the other one has 8 neutrons, right? So then these are still the same element, right? Because the number of protons determines the element and they have the same number of protons. So they're what we would call isotopes of that element. And they have different masses, right? So, let me write some stuff down. Let me give you an example. So, okay. So since I said that there were 6 protons, does someone want to look at the periodic table and tell me what element that is? Or maybe you don't know the names of the elements.
Carbon or anything?
Yeah, carbon, right? Okay. Yeah, I forgot that you guys don't know the names of the elements. So yeah, that would be a good idea. Okay. Yeah, so let's say we have it. So we'll write carbon down. So in the lower left corner, we'll write a little 6 to indicate the atomic number. And let's say that there were 6 neutrons, right? So let's say that there are 6 neutrons. So remember that the mass number is determined by the total number of nucleons. So in this case, does someone want to tell me how many, what the mass number is? Oh.
12 atomic mass.
So the atomic mass is the total of the protons and the neutrons, right? So in this case, it's just 6 plus 6, which is 12. So for this isotope of carbon, we'll write down the symbol as this. Okay, let's do a different example. Let's say we have 9 protons and 10 neutrons. Okay, so can someone suggest what the symbol for this isotope would be?
So it's 5. No, wait. It's F.
Okay.
Right, and then 9 at the bottom and 19 at the top.
Yep. So it turns out that this is the only stable isotope of fluorine. So, and let's just do one final example. Okay. So let me think of a good example. 35 protons, mental math.
So the neutrons can determine whether this element is stable or not, right?
That's determined by a large number of factors. You can, maybe if you want, you can read into the nuclear shell model. Yeah, basically for the lighter elements, you want to have a proton to neutron ratio of approximately 1. But this breaks down as you go to heavier elements, because as you get to heavier elements, you have more and more protons. So the repulsion between them will increase. So we need even more and more neutrons to hold the nucleus together. So let me just, yeah. Okay, so what about the symbol for this case?
It's brass, right?
No, brass is not an element. No.
Okay.
Brass is an alloy of, let me think, see if copper and zinc.
So it's Br.
Yeah.
And then 35 at the bottom and 79 at the top.
Yep. So bromine. So we would call this bromine 79. So okay. Br is bromine.
Okay.
Yeah. And bromine, fun fact. So bromine has 2 major isotopes in nearly a 1-to-1 ratio. Bromine 81. Okay. So I can delete it. So it's, we're gonna get a document camera soon, so I won't have to use Microsoft Paint. So don't worry. In the future, it will be better than this. Okay. It's important to note the sense of scale for the atom. So let's imagine that let's say we scaled up the nucleus to the size of a tennis ball, right? Then how big do you think the atom would be? It turns out the atom would be like the size of the Las Vegas Strip. Okay. So you can imagine how small the nucleus is. And there's nothing in between the nucleus and the electrons, right? There's just nothing. It's really just empty space. So most of the matter around us that makes up the world around us is just empty space, really, which I think is kind of interesting. Okay. Okay, now onto the hard part of the lecture. Okay, well, we already looked at the Bohr model with the electrons going in orbits around the atom. Well, it turns out this isn't really true. So we have to go into a little bit about quantum mechanics. So at these small scales, quantum mechanical effects start to become important. So what does quantum mean? Well, it has to do with quantization, the idea that you can break stuff into little bits, right? So the idea that like energy is quantized. So that means that these electrons can't just have any energy. The electrons have to have certain energy levels, and they cannot exist, like they cannot be in between those energy levels, basically. Okay. So
wait a minute, can you say that again? Sorry.
Okay. So quantization, what we mean is like we're breaking stuff into discrete levels, okay? So, for example, the energy of an electron. The electron can't have just any arbitrary energy. It has to have very specific energies, these very specific energy levels, and it can only have those energy levels. It can't be anything in between. Okay? Does that make sense?
Yeah.
Okay. The second major idea is that matter has wave properties. Okay. So what I want to illustrate is the idea of the Broglie wavelength. So she's from France. So a lot of people mispronounce that as like the broccoli. So that's why I have that written there. Okay, let me just write down his formula. So his formula is that wavelength, which I represent with the Greek letter lambda, equals h divided by p. So h is the Planck constant. Planck, and then p is momentum. So p equals mass times velocity. Okay. And why is this important? Okay. So Planck's constant is equal to 6 times 626 times 10 to the minus 34 joules times seconds. So it's this incredibly small number, right? So for anything on the macroscopic scale, with anything with like a non-tiny amount of momentum, so anything on the macroscopic scale will have some like big momentum, right? So that means the wavelength is like unimaginably small, right? In other words, the wave properties don't matter. We don't need to care about wave properties at the macroscopic scale. However, at the scale of like atoms and electrons, you can imagine that because these little particles have such low mass, their momentum is also pretty low. So that means the wavelength starts to like actually become kind of significant. And it turns out that if you do this computation for like an average electron in an atom, right? So like just give it some velocity, and then we already know the mass of an electron. So we can compute its momentum, and then we do h over that. You end up getting a wavelength that's larger than the atom itself, right? So this electron is somehow a wave. So this electron is somehow a wave that's bigger than the atom, but also in a specific orbit. So that doesn't make any sense, right? So this means that, so basically the idea is that electrons are not in orbits going around the atom. They're in these clouds of probability. Yeah, so they're in these like clouds, these probability clouds that describe where are you more likely to find the electron, but you can't predict where the electron will be. Okay, so this is what the picture I have over here is. Okay, also I want to talk about the Heisenberg uncertainty principle. So, okay. So what this says is that sigma p times sigma x must be greater or equal to h bar over 2, where h bar equals the Planck constant divided by 2 pi. Okay. So sigma p and sigma x are the standard deviation in momentum and the standard deviation in position, right? So all this means, okay, so basically on the macroscopic scale, on like the level that you can see really, sigma p and sigma x are going to be much, much larger than h bar over 2. So this doesn't really apply to classical real world systems, right? But on the scale of atoms and stuff, the uncertainty in position and uncertainty in momentum start to get really small, so it's limited basically by h bar over 2. So basically all I'm trying to say is that if you have like this tiny particle like an atom or an electron, its uncertainty will be significant because it has to be larger than h bar over 2. So we can't determine the position and momentum of stuff exactly. Okay. Okay. Let's move on to the next slide. Okay. So there's one idea I want to talk about. So it's the idea of the wave function. So basically, the wave function, it describes where are you likely to find an electron, where are you likely to find an electron. By the way, it's the Greek letter psi, this letter over here, psi, so you call, okay? And it doesn't really have too much physical significance, but it turns out that if you take the value of the wave function squared, so psi squared, that represents the probability density, right? So it's like how likely are you to find the electron at this given point, okay?
So is psi a unit?
Psi, no, it's
or a constant.
It's not a constant either. It's a function.
Oh, okay.
So this is I think like a differential equation or something like that. Yeah. So this is the very famous Schrodinger equation, and so very difficult to solve. Okay. Okay. So as we said earlier, the electron can only have specific energies, right? Okay. Yeah. So let's see, how do we describe the wave function, right? Okay. Okay, so there are 4 quantum numbers that can be used to describe the orbital, right? Okay. Yeah, so we call these orbitals for yeah, because of the analogy to orbits around the nucleus. But these aren't really like orbits, they're just probability clouds. Also, I want to point out that you might see in the drawing that there's these boundaries on the orbital. No, the orbitals really extend to infinity. It's just that like this is where 90% of the electron is 90% of the time or something like that, the electron's going to be in here. So we draw it like this just to make the drawing smooth. Okay. So these can all be described. What were you saying? Okay, no, okay. So, oh, can you mute your microphone?
Oh, sorry.
Yeah. Okay. So, so so let's move on to the idea of quantum numbers. Okay. So there are 4 quantum numbers that you need to know about. So we call n the principal quantum number. So this really describes the energy of the electron, at least for one electron systems. Okay. Now we have L, which is the azimuthal or angular momentum quantum number. So this describes like what kind of orbital you have in a kind of way. It's like what shape, it's like how much angular momentum does the electron have? Kind of, not really. And then, so, yeah. And it determines what kind of orbital you have. So for historical reasons, we call these the S, the P, the D, and the F orbitals, which come from the descriptions of spectroscopic lines. So S stands for sharp, P stands for principal, D stands for diffuse, and F stands for fundamental, I think. But this isn't super important. So, oh, let's talk about their values too. I forgot to talk about that. So N is any integer from 1 to infinity, okay? So any integer from 1 to infinity. And then for a given value of L, L can be an integer from 0 to n minus 1, okay? So if L equals 0, you have an s orbital. If it equals 1, you have a p orbital. If it equals 2, you have a d orbital. If it's 3, you have an f orbital, and so on and so on. Okay. And this describes like the shape of the orbital.
Excuse me. So is it like a sequence? Because what if like L equals to like 10 or something? Is it still F or?
Okay, so basically after these four, it goes F, G, H, I, J, K, L, M, N, O, P.
Oh, okay.
So I can't, yeah. But I don't know if those don't really matter. We haven't actually discovered any elements yet that have G orbitals. But hopefully, like sometime in the next few years, we will, because we're actually pretty close. And maybe I can show you a big periodic table later. So I'll show you guys a big periodic table later to how far we've gotten. Okay, so M sub L, I can't write the subscripts here. So it's M with a subscript L is the magnetic quantum number. So this describes the orientation of the orbital in space. So like, is it on the X, Y, Z axis or something like that? And the values of M sub L can vary from, they're all integers from negative L to positive L, right? So let's say L was 2, then M sub L could be -2, -1, 0, 1, and 2, right? And then M sub S is the spin quantum number. So I'm not going to try to explain spin. It's really an intrinsic quantity of the electron. And the electron is not actually spinning. Yeah. And the spin quantum number, it's either plus or minus 1/2. Okay. So now we can talk about the Pauli exclusion principle.
Excuse me. So do these quantum numbers have a unit or something?
No, they're just no.
Oh,
they're
numbers.
Okay. So okay. So now we can talk about the Pauli exclusion principle. Okay. So this is the idea, like we have like so all of the electrons in the atom basically have to have different quantum numbers. Okay. We can't have 2 electrons with the same set of quantum numbers. So, okay. So that's the Pauli exclusion principle. And this will become important. This is very important. Okay. Okay. How about we look at some wave functions? Okay. So I'll draw some orbitals too, because that would be helpful. Okay. So let's look at an s orbital. So I want you to get a rough shape of a rough sense of the shapes of these orbitals. So s orbitals are spheres centered. Okay, so they're spheres centered around the nucleus. And okay, so p orbitals are these dumbbell shapes. And D and F orbitals have more complicated shapes, which I'll show you in a minute. Okay. So that's, okay. So let's go back to the PowerPoint for a second. Okay, let's talk about nodes real quick. So basically a node is an area where the electron density is 0. Okay, I'm not saying it's not really small, it's just 0. So this means you're not going to find electrons at a node. Okay, so there are two types of nodes. You have angular nodes and radial nodes. So these are angular nodes, and then radial nodes say like, oh, so some distance from the nucleus, there will just be a 0 electron density. So I think a picture might be helpful. I'll draw a picture later, it might be helpful. Okay, so the number of nodes, the total number of nodes, so the number of angular nodes plus the number of radial nodes equals n minus 1, where n is the principal quantum number, right? Okay. So let's see if, oh, by the way, these are the 5 d orbitals. So they have funny shapes, and the f orbitals have even funnier shapes. So to illustrate this, let's use a p orbital. So, oh, by the way, so in spectroscopic notation, let me write it. Where's the end button here? Okay. So we can designate an orbital like this. So this number here is the principal quantum number, right? And this is what I explained before. It's like the SPDF thing, right? Okay. So how many nodes does this orbital have? Oh, so if you want to, you can just, okay. So this
is it 2 or?
Yeah. Okay. So this orbital will have in total 2 nodes. So I'll just write that down. Wait, why does that keep on happening? 2 nodes. Okay. Okay. So another major point is that the number of angular nodes is equal to L. Okay. Right. So, okay. So how many angular nodes does this orbital have?
2.
Wait. Okay. So remember what I said about S, P, D, and F, right?
P is 2. Right.
So P corresponds. So S corresponds to L equals 0. P is L equals 1. D is L equals 2, and F is L equals 3.
Wow.
Okay.
Wow.
So we have 1 angular node. So first we have 1 radial node. So let's draw this orbital. So first we have this. Then as you can see, we have this angular node. It's like this kind of plane where there's 0 electron density. Okay? So now we have to have a radial node. So let's see if maybe I can draw this in a different color. We can do it like in yellow. So we have this radial node. And then we have another region of electron density further away from the nucleus, kind of like that. Right. So now we have, okay. So as you can see, we have the 1 radial node and the 1 angular node. Okay. So I think now we're ready to move on. Okay. Okay. Oh. So I also want to kind of explain a little more what these nodes are. So let's draw, I'm going to draw a graph, kind of. Black. Okay. So let's say we have a graph. So we have R on the x-axis. So R will stand for radius, so distance from the nucleus. And then on the y-axis, we can just have the value of the wave function. So let's look at an s orbital. So 1s orbital. So, so for a 1s orbital, we have kind of something that looks like this, right? So as you can see, there's no region that the electron density is 0. So the 1s orbital has 0 nodes, right? So n minus 1 is 0, so 0 nodes. Okay, let's use a different color now. Let's look at the 2s orbital. Okay. So we should expect to see 1 node. Oh, but so let's extend that down. So we do. So let me see if I can draw this. So it looks kind of like this. And as you get, so basically, yeah, the wave function can be negative. But when we square it, everything becomes positive, so it's fine. So you can see that we do have 1 node here, right? So this corresponds to our radial node. So when I go to draw the s orbital, the 2s orbital, it looks like this, right? Where this is the radial node, and then we have 2 regions, which and then one of them I'll shade in, and then the other one I'll leave unshaded, because one of them corresponds to a positive, one of them is positive, and the other one is negative. So these are the 2 phases. Okay. And I don't think we need another example since this isn't super important. Oh. Okay. Now we can move on to really the main point of this lecture. So electron configuration. So we have all these orbitals, right? But now we need to fill them, okay? Because like I said, we can only have so many electrons in one orbital, right? Okay. So the electrons fill these orbitals in order of energy, which we call the Aufbau principle. There are some inconsistencies in this order, but we don't need to know about that right now. So this filling orbital, this filling order really determines the overall structure of the periodic table. Okay. And this filling order, handy mnemonic is like Madelung's rule. So this is the idea that you fill orbitals in order of L plus 1. So orbitals with larger values of L plus n, L plus n, fill after orbitals with small values of L plus n. Okay. So, okay. So I want to make another point. Let's imagine we have, let's say, a d orbital. Oh, gigantic fly. Okay. Let's say you have a d orbital. Let's just say it's the 3d orbital. Okay. So can someone tell me what the value of L is?
L should be d orbital, it's 2.
Yeah. Okay, so L equals 2. So given that L equals 2, can someone tell me the possible values of L plus of M sub L?
Excuse me?
What are the possible values of M sub L?
M's of it's 2 or negative 2.
Yeah, so that's the outermost numbers, but it's all the numbers in the middle too. So it's the set negative 2, 1, 0, 1, 2, right? So wait a second. Okay. So I'm trying to manage. Okay. So what does this tell us? How many d orbitals are there then? How many 3d orbitals are there? So we have 5 possible values for M sub L. So that means we can write 5 possible values for the 3d orbital. Does that make sense? Kind of?
Sure.
Right. So, okay. So, what I'm trying to say is that you can make 5 different orbitals there are 5 different possible combinations where n equals 3 and L equals 2. Right.
Excuse me, can you repeat that again?
Okay. So we have 5 possible values for m sub L, right?
Yeah.
So that means that there's 5 different orbitals, right? Because each one of these 3 quantum numbers corresponds to an orbital.
So these orbitals don't like appear at the same time, right? They're like 5 possible, like, or so like they wouldn't like be at the same time, right? Like
No, they're all distinct orbitals that can be filled simultaneously.
Okay.
Yeah, because these orbitals are what we call degenerate, since they have the same energy. Yeah, because remember, all m sub L determines is the orientation in space. It doesn't really determine like the shape or the energy it doesn't determine like the shape and energy of the orbital. Right, so all the orbitals with the same value of m sub L are the same energy. Okay. Okay. Now remember the Pauling exclusion principle that says that, okay, so the spin of the electron is either plus or minus 1/2. So this means that in each orbital, we can put 2 electrons in, right? Because we can either have, a plus 1/2 electron and a minus 1/2 electron. Does that make sense?
So how do we use numbers to identify the electron? Like, how do we use numbers to identify the electrons? Like, why are they like a half or negative a half or something?
Like why is the spin plus and minus 1/2?
Yeah.
Fundamental physical reasons, I guess.
Okay.
Physics is not my area of expertise, so I can't answer that question. But yeah, I guess I think there are general classes of particles, right? Like fermions and hadrons and stuff like that, each of which have characteristic spins. So this might be an interesting topic if you want to read more about it on Wikipedia. Okay. So knowing that each orbital can have 2 electrons, right? And that there are 5 different 3D orbitals, how many electrons do you think we can put into the 3D orbitals?
10.
Yeah, so we can put 10 electrons here. Let's just do one more example since this is important. Wow. Oh, sorry. Oh. I keep on mixing the annotations and the paint stuff. Okay, let's do another 2. So can someone tell me the value of the quantum numbers? Hey, Star, can you mute your microphone?
Yeah.
Okay. So the principal should be 2, right? And then the number of nodes is 1.
Yep.
And L is 1 since it's P. And then so angular node should be 1. And there isn't a radial node since.
Okay, that's good. What about the possible values of m sub L?
Um, it's, be, it's, wait, L is 1, so it's -1, 0, or 1.
Right. So this tells us that how many p orbitals are there?
3.
Right. Okay. Good. And then that means we can have 6 electrons, right?
Yeah.
Okay. So we can put 6 electrons into the 2p orbitals. And this might be a good place to illustrate what I mean by m sub L. So we have 3 orbitals, right? So this means, this is more of a tangent, but it's just a little interesting. So that means we have 1 p orbital along the z-axis. 1 p orbital along the y-axis, and 1 along the x-axis. And these are the py, pz, and the px orbitals. But that's just what I want to illustrate by what m sub L really means. You don't need to actually memorize that. Yeah. Okay. This is that kind of stuff kind of becomes important if you want to talk about like MO theory or crystal field theory, but those are not in the AP curriculum, so we're not gonna talk about that. Okay, so now we can start filling electrons. So I got this nice picture. Let me see if I can zoom out a bit. Oh, the picture's gone. Let me just find one. Let me just get the list so that I don't. Yeah, you should memorize this list, but for now we can just use a picture. Okay, here we go. Okay, so this picture tells us the order that the electrons will fill in, the order that will fill the orbitals, right? Okay, so this tells us that the first orbital to fill is the 1s, right? And then we go by diagonals. So then the 2s, then the 2p, the 3s, the 3p, the 4s, 3d, 4p, 5s, and then you get the idea, right? Okay. So let's look at the. Okay. So let's look at the first few elements. So we'll just go in order. So let's consider hydrogen. So looking at the periodic table, can you tell me how many electrons are in an atom of hydrogen?
There's only the number of protons. Are they the same?
Okay. So remember, so we're talking about neutral atoms, right?
Oh.
So the number of protons and neutrons is the same. Yeah, I forgot to mention that.
So it's 1.
Yep. So we have 1 electron, and what's the first? So let's start with the low. We have to start with the lowest energy orbital. So the first electron to fill is what, right? It's the. So what orbital do we fill first?
The first one. So there's only 1 orbital.
Yeah. Let's just go in order. So we fill the 1s orbital first, right?
Yeah.
Looking at the diagram. And then we put 1 electron in there.
And that's it. We don't have any more.
That's it. Good. Yep. Now let's look at helium with its 2 electrons. So remember, we can put 2 electrons in the 1s orbital, right?
Yeah.
So it's just 1s2, and that's it. Okay, now let's look at lithium. So this one has 3 electrons, right?
Yeah.
So we can do 1s2, but now the 1s orbitals are filled, right?
So it's 2s orbitals, and there's only 1 electron in that orbital.
Yep. So now we do the 2s, and we put oh, my bad.
1.
Yeah, 1. Okay. So now, we have to move on to the 2s orbitals. Um,
Wait, excuse me. Why can there be like two electrons in a 1s orbital?
well, remember that. Yeah, you're right that there's only one s orbital, but each orbital can fit two electrons because the electron spin is either plus or minus one half. So we can put a plus one half electron and a minus one half electron in the same orbital.
So there is one possible m sub.
Alpha, right? There's only one possible value of m sub l,
Yeah,
right?
and
But you
there
have
are
two possible values of m sub l.
Right, right.
Okay. So then what do you think? Can someone tell me the electron configuration of beryllium?
It's 1s and two electrons and 2s two electrons.
Yep. Okay.
The first one is also 2.
Oh,
Okay.
sorry. Yeah. Okay. So what I want you to notice is that we've been so far we've been hanging out in this region of the periodic table, right?
Yeah.
And in that region, we're filling the s orbitals, right?
Yes.
So we call that area of the periodic table the s block. And what I hope to show you guys is that the structure of the periodic table is related to electron configuration. Okay. So now let's do boron, the most boring element, right? Okay. So we have 5 electrons, and we already know to fill the 1s2 and the 2s2. Okay, so now what do we do next?
2p.
Okay, and then we put 1 electron in there, right?
Right.
So now let's just skip to neon. Okay. So can someone tell me what the electron configuration should be here?
1s2, 2s2, and 2p2. No, wait, it's neon. So it's 2p.
Okay, well, let's see. Let's see how the periodic table can help us here. So we start from boron. So boron is 1 p electron, right? With boron, we put 1 electron into the p orbitals, instead of 2 p orbitals, right?
Yeah.
So now for carbon, we add another electron, then another electron, then another electron, then another electron, and another electron. So that's 6 electrons, right?
Yeah, and there can be 6 electrons in 2p because.
Right. So now the 2p orbitals are filled. So in this region of the I have to switch to yellow. Okay. So in this region of the periodic table, we're filling the p orbitals. So we call that the p block. Does that make sense?
Excluding helium, right?
Yeah. Helium can. Yeah. I wouldn't worry about hydrogen and helium too much. Their position on the periodic table is kind of funny. So just yeah. We do this because helium has the properties of the other elements below it. So we put it like there. And then yeah. But we're not going to worry about too much about those minor details. Okay. So let's do silicon. Okay. So what do you think the electron configuration of silicon is?
Wait a minute. So
Okay.
it's 1s2, and then 2s2, and that's for sure. And then 2p6, and then there are 6 left. It's 3s2.
Okay.
And then 3p4.
Wait, so
No, 6. No, 4. Yeah, 4.
wait, how? Okay, so you're almost right. So you're right. We have to start filling the 3p, But okay, so this okay. Let me switch to a okay. Okay, so we're done filling the 3s orbital here, right?
Yeah.
So now we're over here, and this is where we need to start filling the 3p orbitals. So now we have only 1, 2 electrons in the 3p orbital, right?
Right.
So 2. And also, if you want to double check your work, notice that all of these numbers need to sum together to the atomic number.
So sorry, I didn't see the I. I got it confused with the S.
Oh, sulfur? Okay.
Yeah.
Got it. Okay. That's fine. Okay, let's just do a tricky example. I'll just walk you through this one because it's a bit more. Okay. Yeah. Okay, so now let's just do nickel, right? Okay. So now okay. So 1s2, 2s2, 2p6, 3s2. Okay. And now we need to fill the 3p orbitals, right?
Where is this nickel?
Oh, nickel?
Yeah.
Let me circle it.
Oh. Okay.
Yeah. As you study more chemistry, you'll start to like memorize this stuff. So don't worry if you don't know the way around the periodic table yet. Okay?
And then
Okay.
4s2.
Yeah. So now we need to do 4s2 because the 3p orbitals are filled.
And then
How many d electrons are there? So we start from scandium and we count up from scandium. So 1, 2.
8.
Oh, by the way,
8.
can you see the pen icon?
Yeah, I can.
You can see the pen, right?
Right.
Okay.
I can see everything on the screen.
Okay. 1, 2, 3, 4, 5, 6, 7, 8. Right?
And that's the number of no. Yeah, that's number of 3D. Okay.
Yep. So what do you think this block of the periodic table is called?
It's called D block.
Yeah. Okay. Yeah. And this is the F block. Okay. So now let's talk. Is it okay if I clear all this stuff?
Oh, sure. Yeah.
Okay. Now let's talk about how to abbreviate these electron configurations. Because as you can imagine, these electron configurations start to get very long. Okay. So basically, what we do to abbreviate this is we start from, okay, this column, the noble gases, and then we take their electron configurations and we just add onto it. So to illustrate this, let's just start with neon. Okay, neon. 1s2, 2s2, 2p6, right?
Yeah.
Now let's do phosphorus. So 1s2, 2s2, 2p6, 3s2, and then 3p3, right?
Right.
Does everyone see why that is?
I see.
So notice this part are the same. So we can cross that out, and then we can replace it with this. So we put argon and not argon, neon. Neon in brackets, and then we just write 3s2, 3p3.
Oh, so yeah.
So now let's do the abbreviated noble gas. Let's do the abbreviated electron configuration for cesium, which I'll circle on the periodic table. Cesium. So the full electron configuration for cesium would be very long, right? But what's the abbreviated one? Can someone tell me what that would be?
Which line is it on the
Oh, it's the one in the yellow circle.
Yeah, I can see. So it's a bracket RN.
Oh, wait. So you need to add on, right?
Yeah.
So Rn is 86, while Cs is 55. So radon actually has more electrons than cesium.
So it's bracket K. Is that K? Ke?
Oh, that's Xe. Xe.
Oh, Xe. And then it should be 4D1.
Okay, wait. So remember, cesium is in the S block.
Oh,
Right.
5S, 6S.
Yeah, 6s. 6s1. Let me just try to illustrate. Yeah, I picked a bad example. So this is the 1s, then 2s, 3s, 4s, 5s, 6s, and 7s, right?
Right.
Then here we fill the 2p, 3p, 4p, 5p, 6p, and 7p, right?
Yeah.
Here we fill the 3d, 4d, 5d, and 6d, right?
And 4F, 5F.
And then the 4f and the 5f, right? That's right. Just to point that out. So that might help with the heavier elements.
Yeah.
Okay, clear everything. And I think we still need to talk about Hund's rule. So, okay. Yeah, we still need to talk about Hund's rule. So, this has to do with the spin of the electron. So,
S spin?
spin. S-P-I-N. Okay.
Is it like M sub S spin? Is this?
Yeah, M sub S. So an electron with a plus 1/2 spin is usually represented as an upwards facing fishhook arrow. And then for a negative 1/2, it's downwards facing, right? Okay, let's do an example. Okay, the 5d electrons. So how many 5d orbitals are there?
10.
Okay, so we can fit 10 electrons, right?
Oh, right.
But there's only 5 orbitals.
Oh.
Right.
And there are 2 spins. Yeah.
Okay. Yeah, but there's 10 electrons, right? Okay. Okay. So I'll represent these orbitals as these lines. Okay? Does that make sense?
Yeah.
We can give them labels if we want. So x, y, y, z, x, z, squared minus y squared, and z squared. You don't need to know the labels, but they're kind of cool, I guess. Okay. So now let's start filling these. It doesn't matter which orbital we start with since they're all the same energy, but we'll just go from left to right. Okay. So we put in 1 electron. Now we have a choice. We can either put another electron into the XY orbital, or we could put it into a different orbital. Well, it turns out it's more energetically favorable to put it into a different orbital. Yeah. Because you know that electrons repel each other, right? So we don't want to put them into the same orbital unless we have to. And there's the hotel room analogy. So like imagine you and your friends are getting hotel rooms, right? And if you have 5 hotel rooms, you're not all going to go into the same room. You're gonna split it up if you can, and then if you have to, if there's not enough space, you'll start putting the same people into the same room. Okay,